Okay, so what sort of sandbox can you get? So here's this little $99 board. It has this FPGA here in the middle. It comes in different sizes. This is a 500K gate FPGA. That's in theory. The 320 means it has 320 pins around the edge. And you can see it hooks to some memory systems, both a flash and a DRAM. It has connections to USB signals. It has connections to these neat little expansion connectors. If you need to use it to drive a robot or control something, that's what these connectors are for. It has RS-232 and serial and keyboard port and video, which I'll show you in a second. So, and some extra things like for debugging, some switches and some 7-segment displays. So you look at all that and you say, what could I build with that? Well, that question gets answered pretty neat. If you're interested to know what sort of things could one build like this, we build with a little board like this, go look at the 6111, the Introductory Digital Systems Lab website. And that's a project course, it's a junior level lab. And if you look there, you will see that there's a whole series of many years of projects that people built, some of which are quite remarkable. Long before the Kinect was letting you wave your arms and hit home runs on the baseball game, people were building hardware that took a feed from a camera and extracted real-time features from that and used those to drive games and stuff like that. It's a wonderful prototyping environment for doing all sorts of neat things. And if you want to see what the neat things are, go look at the projects there. Some of them are really quite fascinating. What I'm going to do is show you a beta. So here's a little 2-stage pipeline beta that's connected up to a main memory. In this case, it's only a 2,000 location main memory. It has a little keyboard interface with a FIFO, so every time I type a key, it goes into this little end character buffer. It has logic that I had to design that creates a character display, so a little 40 by 80 character display. And finally, the PC shows up here. This is the 2-stage beta. I won't bother you with the details. This looks surprisingly like the slide in the first of the 2 pipeline beta pictures, pipeline beta lectures, where the only distinction being that, remember that the memory has its own internal registers on the address. So all of these wires are, this wire which would have normally, out to get the instruction here, the memory address for the instruction, would normally come from the output of the PC register, but instead I take it from the input. So this is sort of like the Cohen hack, all built in here. So nothing terribly surprising about the 2-stage pipeline. 2-stage pipeline is interesting because this one actually cheats a little bit. It actually has a fake 3rd stage. So what it does is it stalls the load and store instruction. It actually takes 2 cycles in the XE stage. So that means the memory access is just not in the timing budget for a cycle. Okay, so when I take an entire beta, you can see that even for this relatively modest chip, the actual beta circuit is only taking some small percentage of the chip. Right? Suppose you had to design an interesting system, right, that had a huge workload that was basically a multi-threaded or a multi-processor workload. Well, you could use one of these giant Intel Core i7 guys, okay, but compare that to using 1,000 of the little betas, right, which would easily fit in that big diagram. So nowadays there's sort of this trend to marshaling a small army of these simpler processors versus perhaps going off and just building the biggest, hairiest processors that you can imagine that was good at running a single program as fast as you can. And some of the more interesting data center experiments you see these days are people who are thinking about how to use pretty dumb processor chips that are low power and very inexpensive to build these giant data centers. Well, what I want to do here, let's go. This chip is basically completely autistic. Right? All it has is lookup tables and flip-flops and programmable interconnect. You want any behavior at all, then you have to basically program it up. So most of these wires here go directly to pins on this, around the edge of the board. So this fancy VGA interface, it's really wires that go, there's R and G and B wires that go directly to this cable, right? It's not like there's a fancy graphic subsystem here. It's all, whatever fancy graphics there are programmed in here. Well, of course, that's not the only type of digital system you can build. So I'll show you something else that will allow me to talk a little bit about where things are in the modern world. Okay, important digital systems. Let's forget computers for a moment. This was one of those 6111 projects that I mentioned earlier. But this sort of serves to remind us about something, right? Which is, we started, this is a course basically on how to engineer digital systems. And when you think about, you can say, okay, is that important or not? I mean, what's the big, who cares? And the answer is pretty much everything you touch in the modern world is a digital system these days. Almost our communication networks, our information storage and retrieval, our entertainment, our ability to print things to read. It's just everywhere. The control systems for this building, making this room too cold. I mean, that would be impossible without the power of digital systems. So. I hope we've given you sort of a sense, sort of a soup to nuts sense of what it takes to build your digital system. We started with some information, CMOS, sequential logic, FSMs, architecture. We've gone through sort of the whole gamut. But I hope you sort of got a sense of what can be accomplished with the digital system, why we wanted to do digital. My guess is that if you do any sort of engineering in the future that involves hardware, it'll almost certainly involve a digital system of one sort or another. And I hope we've given you sort of a start down the path of figuring out how all that stuff works.